Okay, let's try to solve problem number 79, chapter 23. So the problem says if two positive charges, each with charge q, are held at position x equals to minus a, somewhere like this, and x equals to plus a along the x-axis of a coordinate system or a small sphere of mass m and positive charge q is placed at an origin. This is origin, but it can move freely back and forth on the x-axis. It can move along like f1 and f2, this kind of restoring. It's like a spring, okay, so that you can calculate restoring force. So you have to show that if the sphere is displaced by an amount x which is very very less than a, okay, so it's small displacement and released, it will undergo simple harmonic motion. So simple harmonic motion, I think you are kind of familiar with that. It's kind of displacement and about an origin with an angular frequency given by this omega equals to square root of 4k qk over ma cube. So again, the chapter is electric forces, so you have to use the Coulomb's law again for force F1 along this direction. So if x is a small displacement of sphere along x-axis, so it will be like just some constant k and this charge q and another charge small q times a minus x square. Okay, this is a minus, this is the distance from here to here is a, whenever the displacement is small displacement is x, so you can write a minus x, the distance, that's just r, so it will be like a minus x whole square. So you can, because x is very very less than a, so it's always better to write e minus x instead of just writing x minus a. So for f2, similar idea you can impose, so that's some constant k and the product of two charges and the distance between them. Okay, so clearly you can calculate the net force because these two are just acting in opposite direction. So the net force along x-axis, because there is no movement along y-axis. Okay, so Fx due to two charges q is also a restoring force. I think you are that makes sense to you what the restoring force is toward the origin. So Fx is just a difference of these two forces F1 and F2. So let's try to write this as an equation star. So for small x, if you look at this equation, when x is very small, so that means you can neglect this x, then the expression for f1 and f2 will be same, and you will get fx, the restoring force along x-axis about an origin, will be 0. So we won't be able to find this fx. So we will avoid that by using an expression, by imposing the power series of kind of 1 over 1 plus x square, which is 1 minus 2x, and 1 over 1 minus x square, which is 1 plus. You can look on websites, or even that can this approximation can be found on your book as well. So this is kind of the power series of this form. So we will try to express these a plus x and a minus x like this. If you just take a common of a square on both sides, you'll end up getting this expression, which is 1 plus x. If you just consider x over a as a x dash, let's say, and this as a 1 minus x dash square, so you can write this as this. So it will be a q over a square, so that's 1 minus 2 x, but our x is x over a, minus 1, it will be positives, but due to this negative sign it will be negative. Okay, so I think you are getting the sense of this. So kqq over a square, these two will be cancelled, and minus 2x over a minus 2x over a will be minus 4x over a. So this is the net restoring force along x-axis about an origin. It's like this, the like a spring. Okay, it's like a spring, so along the origin somewhere here, due to the two forces F1 and F2. So you can try to resolve this equation star by taking LCM and try to solve. You will be able to write this kqq over a square minus 2a. This is just a minus b whole square. This is a plus b whole square. You can easily use that, and you will get this. And finally, you can now use the approximation. So if x is very less in comparison to a, so you can write a plus x is like a, because the contribution of x is very small and can be neglected. So similarly, a minus x can be written as a. Okay, so finally this a plus x can be just a, then it will be a square, and next will be a square, so altogether it will be a power 4. So one of the a's will goes out, then you'll end up getting this a cube. So it's like restoring force Fx equals to some constant times x. So you can compare this expression a with the expression from Hooke's law, that is, the restoring force is the negative of spring constant times x. So this is the expression. So here spring constant k can be compared with the expression of a, and you will get k as a 4k. This is another k, so keep eyes on it. So that's why I try to write a different symbol for k. So this is the expression, and finally the angular frequency omega is just the ratio inside the square root. That's omega is just square root of k over m, and we already have expression for k, and so the final expression will be this. So this will be the angular frequency omega, okay, which is the required expression for our problem. So yeah, that's it for the chapter 23. Thank you.